Hello, here's another lecture video for Chem 201 at BBC. This is a continuation of our discussion of electron configurations for Section 4 of Chapter 3 of our online chemistry textbook, Atoms First 2E, provided by OpenStax. In this lecture, we're going to cover a recap of electron configuration. I'm going to go over some key terms. I think I mentioned them in the last video, but I just want to make sure that you have them clearly so they're written out for you. And there's some additional details, I think some exceptions to electron configuration that we need to cover. We're going to talk about the arrangement of the periodic table and then configurations for ions. So hopefully you've had a chance to practice some electron configurations, and I hope that you were able to figure out how to use your periodic table to help you write electron configurations. You want to remember the three different blocks. Actually, there's four blocks, but the ones that we use most often are the S, the P, and the D block for electron configurations. So let's say you wanted to write the electron configuration of the atom that's located here at this position on the periodic table. You should be able to figure this out based on its position. Because it's in the D block, you know that the last electron is going to be a D electron, and because it's in the third box over, it's going to be a D3 electron. And everything up until that value of D3 is going to be completely filled. The one thing that I don't think I clearly covered is that you can follow along from the periodic table to figure out the preceding notation that you would need to use to write down that electron configuration. So we know that we need to stop here. We can begin at the top and say, okay, 1s, we need to put 2 electrons, and then 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d3, and that would be the electron configuration for the element in this box right here. So you just can kind of go from left to right, top to bottom, and follow along on the periodic table, remembering this is going to be the 1s, the 2s, the 3s, this is going to be your 2p, your 3p row, and hopefully you'll be able to build up your electron configuration just by looking at the periodic table itself. Okay, so just some key terms that we need to make sure we have the formal definition for. Electron configuration is a description of which orbitals are occupied by which electrons. The word degenerate or degenerate orbitals are orbitals that have the same energy level. For example, the 3 p orbitals in a given subshell. So the p orbitals are in a subshell, there are 3 of them, and they have the same energy, and therefore they're degenerate. Ground state electron configuration is your lowest energy configuration. So this is where your atoms, your electrons, are occupying the lowest available energy levels of the atom. We have some rules that you want to remember for electron configuration, specifically the Aufbau principle, Hund's rule, and the Pauli exclusion principle. In your Aufbau principle, remember that lower energy orbitals fill before higher energy orbitals. So this is just your basic set of rules for how to create an electron configuration. Remember that Aufbau means build up. So you're starting from the bottom and you're building up in that energy diagram. An orbital holds 2 electrons and they have to have opposite spins. If 2 or more degenerate orbitals are available, we're going to follow Hund's rule, which says that orbitals with the same energy are going to be singly occupied. So we're going to put 1 electron into each until they're all half full. And then the electrons in the half-filled orbitals have the same value of their spin number. Once those degenerate orbitals are half full, and then we'll pair them up. The Pauli exclusion principle states that no 2 electrons can have the same 4 quantum numbers. So they can share 3 out of the 4, but if they do, that means they're in the same sublevel. It means they're in the same orbital, not just the same sublevel, in which case their spins would be opposite. So one would be would have m sub s plus 1/2, and the other one would have m sub s minus 1/2. Let's talk for a minute about valence versus core electrons. So your valence electrons are the electrons that are located in the outermost shell or the highest energy level of the atom. So that highest n value, largest principal quantum number. So you just add up all of the electrons in the highest principal quantum number, and those are your valence electrons. Everything inside of that are called core electrons. Valence electrons are important because they're the ones that are involved in chemical reactions. They're the ones that do chemistry. So we keep close track of your valence electrons. So here's an example. We're looking at the electron configuration for sodium, which is 1s2, 2s2, 2p6, 3s1. Our highest principal quantum number value is 3. Here we have n equals 3. So we would add up everything with n equals 3, every electron in an n equals 3 shell. And clearly we just have the 1. So we have 1 electron in a 3s. But if we were talking magnesium, magnesium would have 2 electrons in its 3s orbital, and therefore it would have 2 valence electrons. Let's take a look at the next atom over after magnesium, which is aluminum. And aluminum has 1 more electron than magnesium. So aluminum's electron configuration would be 1s2, 2s2, 2p6, 3s2, and then we would have a 3p1. And to count up the valence electrons for aluminum, we'd count all the electrons in the n equals 3 shell, which include these 2s as well as this 1p. So it has 3 valence electrons. The core electron configuration can be represented by a noble gas. So the previous noble gas on the periodic table is used to represent a core electron configuration in an abbreviated electron configuration. So the abbreviated electron configuration for sodium would look like this. We would just write neon in parentheses and then 3s1. The abbreviated electron configuration for aluminum then would still use neon because it's got the same core electron configuration as neon. So this much of the electron configuration corresponds to neon. And so then the abbreviated electron configuration for aluminum also uses neon. And then we write the valence electrons, 3s2 and 3p1. We have some exceptions to our filling order because there's a stability associated with the half-filled or a fully filled d subshell. So what's going to happen is an electron's going to shift from the 4s into the 3d orbital in order to create that stability. So let's take a look at copper on the periodic table. Copper is located right here. And if we were going to use what we know so far, we would say it's going to be 4s2 and then it would be 3d9. But because of that added stability of having the full d shell, it actually promotes one of its electrons up into the d shell. So you can see that its actual electron configuration is 4s1 3d10. So that's going to occur for copper, and the element underneath copper, which is silver as well as gold. So everything in group 11 will be S1D10 instead of S2D9. And then the other spot where we have an exception is with the half-filled shells. So for chromium, we would expect a 4s2 3d4, but if we promote an electron from the s into the d, then we can have each d orbital half-filled, and so chromium is actually a 4s1 3d5 instead of 4s2 3d4. That's also true of the elements underneath chromium, so that's true of molybdenum and tungsten. So some things that we want to remember, I went over this a little bit in the last lecture, but just keep in mind that your periodic table is arranged according to things that have similar properties. And so what defines whether things have similar properties is their electron configuration. So the fact that all of the elements in the first column are S1 elements makes them all have similar chemical reactivity. So they were grouped together based on that chemical reactivity, which is a reflection of the fact that they're all S1. So elements in the same group have similar valence electron configurations. And valence electrons, again, play the most important role in chemical reactions and describe why elements in the same group have similar chemical reactivity. Okay, so a little bit more about the periodic table itself. We have different words to describe different regions, the elements in different regions of the periodic table. So we refer to main group elements, also call them representative elements, and those are the ones where their outermost electron or their last electron added is going to go into an s or a p orbital. So they're found in the s or the p block of the periodic table. And these follow our rule for valence electrons, where their valence electrons have the highest n level. So gallium, for example, is a p block main group element. Its outermost electron goes into 4p1, and gallium has 3 valence electrons. We're going to count the 2 in the 4s and the 1 in the 4p when we don't count the d as valence electrons. They count as core electrons, not valence electrons. Now, transition elements and intertransition elements are a little bit different in terms of their valence electrons. They're metallic elements in which the last electron added enters into a d orbital. So when we're adding them, we are moving along the periodic table and we stop at a value of a d. And their valence electrons are going to include ns, so the highest n value in the s, but n minus 1 in the d. So for example, vanadium is 4s23d3, and we count it as having 5 valence electrons. Our intertransition elements are also metallic. In this case, though, their last electron occupies an f orbital. So these are these elements down here. They're called the lanthanide and actinide series. And when you're putting electrons in, the last electron for these elements are going to be allocated into an f orbital. So we call this the f block. And so their valence electrons are n sub s and then n minus 2f and sometimes n minus 1d. So it gets a little bit complicated with them. But here we have an example, promethium. I always want to say paramecium, but promethium, which has 6s2 and 4f5. So we see it has a total of 7 valence electrons. So what we do is we find the biggest principal quantum number, and we count the s electrons for that principal quantum number, and then we subtract 2 from it and count f electrons for the n minus 2. So we have 2 in the 6s and 5 in the 4f for a total of 7 valence electrons for promethium. Last thing that we're going to talk about in this lecture is the electron configuration of ions. Remember, ions form when atoms gain or lose electrons. A cation forms when an electron is removed from an atom, and when this happens, it ends up having more protons than electrons, so it has a net positive charge. For main group elements, the electrons that were added last are the first electrons that are removed. Now for transition elements and intertransition elements, the highest n sub s electrons are lost first, so they're the ones that are removed first. And then n minus 1d or n minus 2f are removed. Usually, it usually is just those n sub s electrons, but sometimes we'll see others. Actually, I'm going to take it back because I think we have a pretty good variety in this class of the ions that we see. So usually they'll lose their 2 ns electrons. I'm trying to see, where am I pointing? Yeah, there it is, ns. They'll lose their 2 ns electrons, and then if they're going to make a 3+ cation, they'll lose an electron from d. Or if they have f electrons, they'll lose an f electron. Let's take a look at an example of that. So let's look at the electron configuration for, let's look at iron. So the electron configuration for, okay, we should probably start simple. So let's just start with sodium. We'll look at the electron configuration for sodium first. For the sodium ion, I mean to say. So looking at sodium, its electron configuration is going to be 1s2, 2s2, 2p6, and then 3s1. And the most common charge for sodium is a 1 plus charge. So it easily makes a sodium 1 plus cation, in which case it loses 1 electron. So it's going to lose its outermost electron. Its electron configuration will be 1s2, 2s2, 2p6. Looking at phosphorus, we have a 3 minus charge. And I think I might not have read that part of the slide, but an anion is a negatively charged ion, and it forms when one or more electrons are added to the parent atom. And these electrons are going to add to increase the number of electrons beyond the number of protons in the atom, and therefore it will have a net negative charge. We're going to add the electrons according to the Aufbau principle, so just the way you would if you were writing an electron configuration for any other situation. So looking at phosphorus, has what electron configuration? So let's look at its position in the periodic table. Phosphorus is located here, so it's in the P block. It's in the third row down, so it's a 3p, and it's in the third box over, so it's going to be 3p3. So I need to fill in everything up to 3p3. So it's going to have 1s2, 2s2, 2p6, 3s2, and then 3p3. And so we're trying to write the electron configuration for phosphorus 3 minus. So it's going to add 3 additional electrons, and its electron configuration would then be 1s2, 2s2, 2p6, 3s2, and then 3p6, because we can put 3 more into the p orbital, into the p subshell, I should say. Okay, so let's do the next one that I wanted to do was the iron 2 plus, and this is kind of the interesting case because the electrons that we're going to remove are not the last electrons that went in. So let's write the electron configuration for iron. We need to know the position of iron on the periodic table. Let's see, we have it right here. Okay, so it's in 1, 2, 3, 4 period, except that it's in the D block, so we need to subtract 1 from 4, so we'll get that it's going to be 3D, and it's in the 1, 2, 3, 4, 5, 6th column over within the D block, so it would be a 3D6. So we're going to fill in the electron configuration up to 3D6. We're going to start with 1s, then we'll go to 2s, and then 2p. We'll go to 3s, and then 3p. We'll do 4s, and then we'll do 3d6. So it'll look like this: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then 3d6. And so what we know is that when iron loses electrons to make a cation, let's say it's going to make the 2 plus cation, it's going to lose the s2 electrons first. So sometimes you even see the electron configuration written down with the 4 s2 electrons written last. But either way, when you're going to write your cation configuration for a transition element, you're going to remove the highest n level s electrons. So 1s2, 2s2, 2p6, 3s2, 3p6. And since we're removing both of the electrons, right, we're going to make a 2 plus charge, so it's going to be deficient by 2 electrons. So we're going to lose both of the electrons in the 4s orbital. So we're not even going to write the notation for the 4s anymore. We're just going to write 3p6, and then we'll write 3d6. So this would be the electron configuration for the iron 2 plus ion. So that's how you write electron configurations for ions. And that's all I've got for you for this lecture. So the next lecture is going to cover the next section. And as always, let me know if you have any questions. Bye for now.